An optical fiber is made up of three parts. The first is the coating. Made from plastic materials, the coating provides protection against bending, damage to the glass surface, environmental effects, and mechanical stress. Depending on the application of the fiber, different types and diameters of coating can be applied. Most optical fiber receives an acrylic coating to a diameter of 250 microns. This coating can be tinted with colored inks and is commonly used in outdoor cables. An additional layer of coating can be applied to achieve a diameter of 900 microns, used in indoor cables including breakout and distribution, as well as fiber cordage. Coatings are applied as part of the fiber manufacturing process and are usually UV cured, whereas colors and additional buffer materials can be applied during the cabling process. In every optical cable, it is necessary to quickly and accurately identify individual fibers. The EIA 598 standard specifies a 12 color code to be used on fiber coatings as well as buffer tubes, or subunits containing individual fibers. Under the fiber coating is a layer of cladding, usually made of pure silica glass. The function of the cladding is to prevent light from leaking from the fiber core. While most fibers used in communications have a cladding diameter of 125 microns, fibers are available with 140 micron cladding. With some of the step index profile fibers, claddings up to 1,000 microns are not uncommon. Beneath the cladding, the core is the part of the fiber that carries the optical signal. Like the cladding, the core is also made of silica, but is doped with certain elements to change its refractive index with respect to the cladding. In a multimode fiber, the difference in refractive indices between cladding and core forces light to be totally internally reflected along the fiber waveguide. In a single-mode fiber, the distribution of optical energy takes on a Gaussian profile, with approximately 80% of the optical energy traveling in the core and the remaining 20% traveling in the cladding. With both fiber types, light launched into the fiber within a small angle of its axis will be transmitted to the opposite end. The maximum angle that a light ray can have and still be captured and guided by a fiber is called the numerical aperture, which defines a cone of acceptance at the fiber's end. Light that enters the fiber from outside the cone of acceptance will not be transmitted, but instead will be refracted out through the cladding and lost. Fibers with large numerical apertures make it easier to couple light into the fiber and are more suited to propagate light from lower-cost, large-area light emitters like LEDs. However, these fiber types are limited to lower bandwidths over shorter distances. One example is Boeing's 777 aircraft, which uses 100-140 multimode fiber in both the electronics bay as well as the passenger entertainment consoles. This fiber has a numerical aperture of 0.29. Multimode fiber such as 50-125 has a smaller numerical aperture of 0.2 and is capable of much greater bandwidth over longer distances. Since it can couple light from small area emitters like laser sources, it is much better suited to high-speed local area networks and storage area networks using protocols such as 10 gigabit Ethernet and Fibre Channel.